This is a tutorial to develop the demand process generator for the Cafe Java example using the inverse transform method. This tutorial is going to be using two external packages, which I'll first import into this Python script. The first one is import the Numpy package, which I'm going to refer to as a shortened name NP. And I'm also going to import the matplotlib.pyplot package for some plotting capabilities. I'm going to give that the shortened name PLT. Now in this example, there are 4 different sizes of demands for coffee. I'm going to store these in a variable named demands, and I'm going to use the Numpy array constructor np.array and passing in the list of these 4 sizes as discrete or integer values, 0, 1, 2, and 3. Now these 4 sizes are terrific to refer to as integers for some of the mathematics side of the script. But to make things a little bit easier with the plotting, I'm also going to create a variable called labels, which I'm going to store in a plain array the strings none, small, medium, and large. These 4 elements correspond to these 4 integer demands, which will be used to give the plots a nice meaningful label. Now in the framing of the problem, the observed demands for these 4 sizes are given. I'm going to store these observed demands in a variable called frequency, again using the Numpy array constructor and passing in these observed frequencies. In this case, 8 customers were observed to order no coffee. Maybe they wanted a tea or a hot chocolate. 10 customers demanded a small coffee, 22 a medium, and 10 a large. Now the first part of this problem asks to develop a probability mass function to describe the demands for these 4 sizes. The probability mass function is a pretty straightforward thing to compute given these frequency data. I'm going to create a new variable PMF to store the results of this computation. And to compute the probability, I'm going to take each of these entries that have been observed for frequency, for example, 8 orders of no coffee, and divide it by how many total orders were observed, which is 8, 18, 40, 50 total observations. Writing this using the Numpy packages, I can divide the frequency array by the Numpy sum of all the frequency elements. So if I run this script as it is thus far, I can start to inspect some of these variables. I can see the demands variable has these 4 integers in it. Labels has these 4 labels stored. Frequency has these observed frequencies. And finally, the PMF probability mass function is, well, looks like we have a problem. Our old friend, the integer round off errors, has come to strike again. And what we need to do is actually cast one of these variables, either the numerator or the denominator, as a floating point. Easiest way to do that in our script is simply to use the word float and surround it around the sum of the frequencies. That'll convert this 50 from an integer to a floating point number and remove some of these round off problems. So let's take a look at that probability mass function again. It appears that 16% of the observations ordered no coffee, 20% small, 44% medium, and 20% large. I think we're well on our way. The next thing we want to do is maybe consider plotting this probability mass function. Using the Matplotlib library, I'm first going to create a new figure, plt.figure. In this case, I'm going to use what's called a bar plot, plt.bar. This will create what appears to be a histogram or a probability mass function display. This bar function, if you inspect the object inspector entries by pressing Control-I, for example, will show you that it expects a couple of different properties, one of which being the well, the left is the x coordinates of the left sides of the bars. The height are the heights of the bars. So in this case, what we're going to use is actually these integer demands to store as the x coordinates of the plot. So if I first start creating a bar plot at these x locations, so 0, 1, 2, 3, and the heights of the bars, we want to use the probability mass function, PMF. If we run this as it is, we can see that we get a pretty nice plot. It's displaying about 16% for the entry corresponding to no coffee, which is at that demand number 0. We can make this look a little bit better by changing this bar width, for example. So we can specify an explicit value for the bar width as the next parameter. So for example, we may only want bars to be half a unit wide. You can take a look at how this changes the plot. Now their bars are a lot skinnier, and they only fall between the demand index and the next half value. All right, now let's add some labels to our plot to make it look a little bit better. I'm going to assign the plot y label to display p of x for the probability mass function. The y limits I want to set between 0 and 1, just to be consistent with the possible bounds of probability mass function entries. Get some updates here. So now our plot ranges from 0 to 1. May also want to set the plot x label to coffee demand, which is our random variable x in this case. And the other thing that we may be interested in setting is another property called x ticks. This lets you relabel the numbers that are actually labeled, the tick marks at the bottom of a plot. So in this case, we may want to use our x ticks to only write the ticks at the location of these demands. And we want to use the labels that we had defined up above. So this x ticks function takes 2 arguments, the location of the labels and then the strings that should be supplied at those locations. So now we see that we have none, small, medium, large displayed at 0, 1, 2, and 3. And perhaps we just want to shift this over by maybe 1/4 of a unit to get our labels centered in the middle of the box. All right, our probability mass function is looking pretty good. The next step that we can think about is then moving on to the cumulative distribution function. The cumulative distribution function, as we discussed in lecture, has a fairly simple functional form. We just need to add up sequentially or cumulatively the value of the probability mass function. So the cumulative distribution function for none would be 0.16. For small would be 0.16 plus 0.2. For medium would be 0.16 plus 0.2 plus 0.44, and etc. Unfortunately, in Numpy, there's a very convenient function to do this called cumulative sum. And in this cumulative sum function, that's one argument is the array that you want to perform this cumulative sum operation on, which in our case is the PMF. So I just want to test this to see that it actually works. I'm going to type in CDF into our console. We see that we have this nice cumulative summation. So the first entry is 0.16, next entry is 0.36, which again is 0.16 plus 0.2, and et cetera, et cetera. All right, let's create another plot for our cumulative distribution function. I'm going to use Matplotlib to create a new figure, plt.figure. This time, however, rather than using a bar plot, I'm going to use what's called a step plot. Because this is a discrete random variable, the cumulative distribution function takes very sharp jumps at each increment in the random variable value. So the PLT function that we want to use again is step. This has similar arguments to other plotting functions. The first argument is the x location of these steps, which is the demands. The next argument is the function to be plotted, which is CDF, the cumulative distribution function. And the third argument is actually the mechanism by how steps are computed. And in this case, this uses a keyword where, and in the case of cumulative distribution functions, those steps happen after the discrete value. So it's considered the post where value. So if I run this script right now, we can see that the value of this function that's being plotted is 0.16, right at 0, which is the value for none. And then right when it gets to the small value of coffee, it jumps up to this 0.36. So this cumulative distribution function is looking exactly how it should. I'm just going to adjust some of the labels again. I'm going to change the y label to capital F of x for cumulative distribution function. I'm going to change the y limits to 0 to 1 for consistency. And I'm also going to change the x label to coffee demand, which is our random variable x. And finally, redefine the same x ticks as before. I'm just going to copy and paste this previous command that we used to write the x ticks. But rather than shifting those labels over by a quarter unit, I'll just display them exactly at their demand location. So now we can see by running the script again, our nice cumulative distribution function. And looks pretty good. One thing I guess we could do to change this a little bit, it's hard to see how the cumulative distribution function changes at these extremes, at none and large. So perhaps I'll just change the x limits of this to -0.5 and 3.5. That'll give us a little bit extra space on the left and right hand side to see how the plot actually changes. All right, so it looks like there's a couple of artifacts missing here from the none, and the final line here is missing at the large, but you can get the general idea for cumulative distribution function. All right, the next tasks that we have in this problem are to generate a number of samples that draw from this cumulative distribution function or from this distribution using the inverse transform method. Now this inverse transform method I'm going to store in a separate function, which I'm going to define, def, and I'm going to give it the signature generate underscore demand and colon to finish the function definition. Now in this function, if you remember the steps of the inverse transform method, the first step is to generate a random number, r, and this I'm going to generate from the numpy.random.rand function, which will give us one number floating point between 0 and 1. Then we have to check successively whether this r value is less than each step in the cumulative distribution function. And if you remember back to our cumulative distribution function, it's really just this array of 4 elements. So the first thing we want to do to check is if that r value is less than or equal to the first array element in this cumulative distribution function, 0.16. So if r is less than or equal to CDF index number 0, then we want to return whatever demand this corresponds to. And in this case, it would correspond to if the random number is between 0 and 0.16, it corresponds to the none demand, which just happens to be demands index 0. Now we have a couple of other cases to check. The next else if check is to see if r is less than or equal to the next entry in the cumulative distribution function, which is CDF index 1. And similarly to before, if we know that r is not less than 0.16, so we've already ruled that out, otherwise this little bit of code would have finished up this function call. We now know that it's somewhere in here, this range between 0.36 and 0.16. So in that case, we know that we can return the small size of coffee, which is demands index 1. We can follow the same procedure to check if r is otherwise less than CDF index 2. And if so, we can return the medium demands. And finally, the last case, if it's not less than this third entry, 0.18, we know in all cases that we can return the final demand, demands index 3, which is large. All right, so we can run our script. No changes in the console, but if we do type in the console, generate demand, it'll try running this function. This particular time it returned 1. If we remember back to our mapping of demands, 1 corresponds to small. But each additional time we run this, we'll get a different result, 1, 1, 2, 3, 3, and so on. So these all correspond to the different demands that have been generated from this probability distribution function, again using the inverse transform method. So now we can use this generator to generate some samples. And in particular, maybe we want to generate a number of samples, let's say 1,000. So I have a variable that I've just created, num samples. I'm setting it equal to 1,000. And I'm also going to create some space to store the result of these samples in a separate variable, samples. And I'm going to initialize it using the numpy.zeros function. This will create a blank array with a certain number of elements in it. And in particular, I'm going to create this with the num samples size. So if I run this script and take a look at the samples variable, we see it's just a very long list of 0. So looks good. Let's fill this up. So the last little bit that we'll do for generating these samples is to iterate over all 1,000 samples, or all 1,000 desired samples. So I'm going to use a for loop. So for each sample, I'm just going to call it I to be simple. It says a temporary variable, a placeholder, an index. For I in the range of the number of samples. So range is a Python function that automatically enumerates all of the numbers between 0 up to some upper limit, like 1,000. I can try this, for example, looking at the range of 10, and it gives me the list from 0 to 9. Range of 20 gives me another list from 0 to 19. So here, range num samples will give me a list from 0 to 999. So inside of this for loop, I want to generate a demand, and I want to store this generated demand in the index of the samples variable corresponding to the current index, or I. So samples index number I is going to be written to be this newly generated demand. So I can run this script and take a look at the samples variable. Now, rather than just being all zeros, it has a distribution of none, small, medium, large, corresponding to our inverse transform method generator. And we may want to visualize this, for example. We could generate a histogram of the frequency of these 4 samples. But what we can actually do is also you create a bar plot and compare the observed generation frequency with that we would have expected from the observations we'd made previously. So to make this a little bit easier, we're first going to create 2 other variables. 1 is just going to be the count of the number of zeros, the count of the number ones, the count of the number twos, etc. So I'm going to create a variable called counts, and I'm going to use a kind of complex function here to count up the number of instances of each value in these samples that we just generated. And to assign this, I'm going to use first the Numpy array constructor. So that's going to create a Numpy array. And inside of this array, I'm going to give it a generator function to automatically create this counting sum. What we really want to do is we want to find the sum of those samples that are equal to some number I. So we could test, for example, the sum of samples that are 0, the sum of samples that are 1, and the sum of samples that are 2. And what we'd really want to do is to take 157, 203, 440, and whatever it is for the large size coffee and put them together into one list to make it easier to plot. We can do that in one line by using this variable I, running this computation of the sum of the number of samples that are equal to that variable, and just repeat that multiple times using the for notation for I in demands. So if we just type here in the console, for example, I for I in demands, but put it inside of a bracket to allow it to be a generated list, I for I in demands. This just lists out all the possible values of I as it corresponds or as it takes on values from the demands list. So as that notation is used here, it's taking the sum of all the samples that are equal to this value I for all the possible values of I given the different list elements in this demands list. So if we run this completed code real quick, we can take a look at the counts. It looks reasonable, about 200 none, about 200 small, about 400 medium, and about 200 large. That corresponds roughly to what we'd expect from the probability distribution. But to plot this, we may also want the frequency. So I'm just going to create another variable called fraction. And here what we want to do is to take the number of counts and divide by the sum of all of the counts, which again we know is 1,000. We know it's the number of samples, but this just is a convenient way of representing that concept. Now again, we have to be careful of floating point round off, so I'm going to surround the sum of counts using the float assignment. And we can run this again. And the fraction that we've observed in our simulated samples, our generated samples, is almost 20%, about 20%, about 40%, about 20%. So finally, we can compare this against the original observed data. I'm going to use another plot. I'm going to use Matplotlib to create a new figure. And then plot using the bar function and then the x-coordinates of demands, our original probability mass function. I'm going to also make the bar half a unit wide and give it the label theoretical, or actually I'll use the label observed. This is what we originally observed in our data. However, we want to overlay a second plot using another bar chart and the same demands x location of our fraction, same half unit bar width, that we've generated using the inverse transform method. And finally, I'm going to just actually probably just copy and paste some of these previous settings that we used for the PMF plot. Y label of P of X, Y limit between 0 and 1, X label coffee demand, and X tick locations at those corresponding locations. Now the one thing that is missing here is that we haven't changed the color of the two plots. And we also are, these two plots are actually being plotted on top of each other because they're both using the same x locations for the center of the bar. So what I'm actually going to do is offset our generated demands by half a unit. So that just pushes them over to the side. And now to recenter our labels, I'm going to move the labels to be offset by a full half unit. So that moves them in between the two. And finally, I'm just going to change the color. Maybe I'll set the color optional parameter for the theoretical or the observed to black or K. And maybe I'll set our generated to green. Color equals green, G. Okay, so now we have these comparisons of the number of originally observed and then generated for none, small, medium, large, and it looks pretty accurate. Now in a future discussion, we're going to, in next week's lecture, we're going to discuss a statistical test to compare whether these, there are some slight differences here, and we'll use a statistical test to see if that difference is